Hello, my microwave and RF designers, engineers, researchers, scientists. Good afternoon, good morning, wherever you are. This is Dr. Mohammed Nizami with another one of my presentations on RF radio frequency and microwave device 3D modeling and design and simulations. I have been doing a bunch of these presentations on topics varying from waveguides to transitions to waveguides, from planar lines, filters, microwave filters, be it waveguide filters, microstrip filters, suspended line filters, and radar combiners, a whole bunch of other designs. You can refer back to my videos and share them, distribute them so that everybody benefits from them. Today, I'm going to talk about a tiny little device that we have been seeing more and more often use of it, which is RF crossovers, okay? And from the name RF crossover, it really means it's basically building, since RF boards nowadays becoming very dense for like applications for 5G transceivers, 5G amplifiers, radars for vehicles, SATCOM terminals. So there's a lot of need to integrate more and more in a smaller area. So we've got cases where we have multi-layers board that we need to somehow get the signals. There's a point where the signals come in and they have to jump over each other to continue. So to make this happen, we have to design a crossover. Crossover meaning, two signals that, or even one signal that comes in and it has to somehow avoid be touching another line. So that has to be designed carefully, since we're doing a lot of stuff at millimeters, X-band, down in the S-band, L-band, maybe one could just punch a via and transition down to a lower strip line and then go back up. It doesn't have to be super duper designed, but carefully laid out. But as you get higher and higher into frequencies up to Ka band and beyond, crossovers are a real challenge to design. So let's talk about crossovers and basically what it is, just like you see on the screen in here. It's basically two signals where one signal comes in here, another signal comes in here, and then all of a sudden there's another signal that has to go this way. And just like intersection on cars, somehow one has to, we can't really stop signals, wait for this one to cross. That would be nice. But we have to go in and just go down below to another layer, to a strip line layer. In this case, this is probably not shown in here. Let me just show it. Okay, there you go, one more. So this is where the signal somehow has to come down and transition to a sublayer and then cross over and then go back up on top again. So this is a device that I designed. We will talk about this towards the end, but let's start the lecture here, or the presentation. Now, again, just introduce myself. This is Dr. Mohammed Nizami. I'm an RF microwave independent contractor. If you need hire me for any job that you have, I come in and I operate relatively inexpensively. So you could reach out to me at this number or at this email. So you can design stuff from DC all the way to 35 gigahertz. I have also an ongoing training that I'm doing. There's 3 different trainings, but one of them is on the RF and microwave device design and 3D modeling, which is basically these videos. You click down on these videos, If you come into this training over 3 days, for the price that is shown on here, you sit down and you work yourself from the ground up with my assistance, with others as well, to design these devices, learn their theory, learn advanced features of the ANSYS HFSS, and then construct these devices for fabrication and manufacturing. So if you want to come, you want to get some information on the on registering for one of these, please let me know. Just email me at this address. So today's lecture, we come to today's lecture, and what it is basically, it's RF to RF signal PCB crossover designs. Now, like I said in the beginning, this is where you have two signals, and somehow one have to cross over to the other side without touching this, shorting to the signal. So we use a crossover to perform this function. And symbolically, that's like this here. So the two signals, one signal goes this way, another signal has to jump over and go that way. And of course, while this can be easily done in low frequency and DC with like a 0 ohm resistor, or an inductor, you might say. Unlike that in RF world, we can't do that at higher frequencies. I know we could do it at lower frequencies, sure, we've done it. If you have use not an 0201 package, but let's say an 0805 package, an inductor or resistor, 0 ohm resistor, and you could sneak a line underneath it and cross over to the other side. That's done it in the past on boards. There are for products in the 1.5 gig or 2.4 gig, low cost stuff. Now, these just recently, within the last several years, there's many companies that started fabricating packages or chips for these because they're becoming more and more, and you get occasions where somebody doesn't want to do a design on this, doesn't want to design it into the board, but rather use a package to do that. And one of these is, this one is used to be Anraen, this company, now it's TTI or something, but their Zinger product line, that's a jump over. So as you can see here, one of the signals goes in here, and in a strip line, it goes to the other side, while the other one is microstrip line and it goes on top. So that's what you see in here. See, RF in out, in out, and on this one, in out on this side, and in out. Same way on from Florida RF Labs, and I think this one is now not anymore RF Labs, Florida RF Labs, but Smith Interconnects probably. So these things, you can see them often, and they're usually somewhere to like 6 gigahertz. And so they're limited. So today I'm going to show some designs that go way to the Ka band. And that, of course, to do that, you have to design it into the board using relatively not so inexpensive substrates, where this one here, it might be an FR4, although they say in here substrates such as FR4 and G10 and RF35 and Rogers 4003 and polymer. Well, they're saying compatible with, but they're not really the same. And that's probably why they're limited to 6 gigahertz because of the loss. Okay, so another company is AVX. And this again got purchased by Kyocera. Same thing, 6 gig. And now some of them are one-way jumper. So they're like, this one is one way. And I think this is 2 ways. This is one way, as you can see here. There's only one connection that you can see that clearly it's a strip line or a microstrip line. Okay, so let's see, how do you go about designing one of these in the board? I don't want to, when you have a board that you're designing, say for SATCOM transceiver, a receiver or transmitter, and you at the beginning, you choose your stack layer, and you finalize that. And then somehow you have to way at the beginning, you have to establish these things, and you say, I do want, you come up with a map for the vias into the stack layer. So at that point, you will have to somehow eventually specify and design a crossover, or some people call some of these via transitions, or via transition from microstrip line on top to a strip line embedded between two ground layers in the middle of the stack layer. And so you have to design that, and once you design it once, that's it. It becomes a component. So you could actually assign a symbol to it, and then the PCB layout engineer, be it you or somebody else, would just basically reuse that over and over and over and over. But before that, you really have to design it and model using 3D modeling to try to make sure that it works and it performs. Now, considering the fact that, let's start out and just refresh our minds of the three typical transmission lines that we use in printed circuit boards. Okay, these are the ones that make up the individual entries into the stack layer, the board stack layer. The most famous one, of course, you're familiar with this, which is the microstrip line. That's where you have a line on top with a certain width, and you have a ground beneath it, and becomes a reference to it, and that becomes a microstrip line. And there are formulas and rules to design that. It's pretty common, and many of you have used it, of course. The other one is a coplanar waveguide, and that's nothing but the same as this here, except it's bounded by two ground strips on top. These could be copper core, or they could be strips of copper that go along the what would be at one time microstrip line. In this case, it's a coplanar waveguide, or a grounded coplanar, because there's grounds. And of course, the copper on top that is shielding this line has to be commonized to the copper on the bottom of the board, which is ground, and that's where we use vias. And they're nothing but rods of copper, or cylinders of copper that goes down and interconnect top to bottom with this using PCB techniques. Another one is the strip line. A strip line is nothing but a same as microstrip line, okay, but sandwiched between two ground layers, one on top, one on the bottom. And you can see, so this one is exposed to the ambient, where this one is not, is bounded. This one is exposed, this one is not. This is inside. So a lot of times when you're doing a jumper, meaning you have to jump over another signal, there's no way to jump on air. You have to somehow go down beneath, and that's where the signal transition would have to be done from microstrip line to strip line and back up, or from coplanar waveguide, grounded coplanar to strip line, and then back up to either coplanar waveguide or to microstrip line. And that's basically the basic element in building a crossover. If you review the literature, there's so many people that design these for various applications. But usually they go like this, okay? You've got two lines that come in and use via to transition down beneath, either to the other side of the board or to a microstrip. So it could be that you have a microstrip at the bottom, so the transition to that, and then go a little bit past the intersecting line in here on top, and then come back up. Same way they can be done like this, and usually there is a we design it, and the challenge is to design a few via ground vias, okay, that interconnect the ground on the second layer that you're jumping to, and mimic in that case. Your job is to make it mimic as if it's really a connector type. Okay, in fact, they have a name for it. It's a quasi coaxial connector in PCB, which means you design a via and a certain pattern of ground vias around it to mimic a coaxial line. And you could set that up so that the inner diameter of the board material between surrounding the bounded by the ground vias and the diameter of the via itself, you could design it such that you can actually preserve and implement a 50 ohm. Another technique which is interesting, but it takes a lot of landscaping, is basically to come in and use two quadrature couplers, okay, back to back. And what that does, if you now usually in a single quadrature 90-degree hybrid, you come in here and your output would be here in this case, okay? So you're really coming in here, and you come, and this one in here, and you come in here, but you split three ways. So this would be the same signal that you put in here would split with 90-degree. But what we want to do, you could construct back to back two hybrid 90-degree hybrids, where if the signal that comes in here actually get out on this side completely, and it's isolated on this end, okay? And by doing this, you really implemented a jump over or a crossover, okay? Because the signal in here has to go past this one here without, and in this case, this is all planar, so all in microstrip. If you can afford the landscape of this, sure, yeah, this is easy to do and works very good. Now, lately, there has been a lot of people that looked at this and said, well, if I'm gonna, like in my case in here, for instance, I have a 3 millimeter by 6 millimeter crossover. Some people say, well, since we have to do this business of crossovering, why don't we utilize some kind of pattern to resonators to do actual filtering? And so it becomes almost like a diplexer, not only crossover, but it's really a diplexer. And you can find in the literature, some people did this, and a lot of people are working on this. And these usually, they come in two types, either microstrip or substrate integrated waveguides, as I will show in a minute. So what this class of crossover code, it's really filtering crossovers, meaning it's a crossover, but it does filtering as well. And in this case, for instance, look at this. This might be done for to combine a 5G with signal with Wi-Fi, where this signal here has to cross over to the other side, and you do it this way, and you do the 2.4, it comes out here, and between these, theoretically, it's completely isolated, but physically, really, we end up with a good amount of isolation in the beyond 30 dB. Okay. And there are various ways of implementing this. Okay, in this case, they're implemented with a resonator that has sides loaded with open stubs. Okay, that's to shrink the size of the resonators. Okay, another ring resonators they call them. Another one that is like this in here, shown in here, and you can contact me if you want to find these in the literature, locate them, but they're in the IEEE publication sets and other conferences as well, and on ResearchGate. But just type on Google filtering crossover RF. Crossover is one word. I apologize for the typo here. Okay, so there is another whole set of this, which is based on substrate integrated waveguide. And what that is, let's look at this. This is simpler one. There's 4 of them. This is not the same one. This is 4 examples of this. Let's look at this one. And that was where you can design a crossover so that you come in here and you go out of here, and these two are isolated. Likewise, you can come in here and go out here, and these are two isolated. And that's basically designed using a substrate integrated waveguide with a pattern that basically performs, might say, multiplexing or diplexing. And this can be done for more higher than just 2 signals. Like in this case, this is 6 signals. So in essence, this is really a switch matrix. because you can come in here and you can have signal that goes in here, goes in here, goes in here, goes in here, and you determine which one goes that way. So it's pretty good. It works really nice when you read about it. Other two variants, the same as well, okay? So basically, what it is you basically design these via irises and the irises and the vias, determine the isolation between these boards, between these terminals based on the modes and resonating dimensions, okay? So that leads us to doing via-based RF signal, RF to RF signal crossover in the PC board. And that's what I'm going to do today as an illustrating example. What I did is first of all, I assumed that I have a case where, let's say that I have this board where I came up with the stack layer, which is a 6-layer board in this case, okay? And the 6-layer board that I'm using right now today is basically made of 3 cores of 4350B, okay? And of course, I have to sandwich these. So they're sandwiched and glued together or bounded together with 2 pre-preg layers, and they're from this material, which is all Rogers. This is RO4450F, which has a close dielectric constant to the Rogers 4350B. So what we have 6 layers. So we have copper 1, copper 2, copper 3, copper 4, copper 5, copper 6. So we have the bottom, the top, and then inner coppers, and then we have the cores, okay, 3 cores and 2 pre-pregs. And so what I'm going to come in and say, okay, I want to implement macrostrip line on top here. So this layer here, L2, will have to be grounded. Same thing on the bottom. I want to design macrostrip lines on the bottom. Okay, so the one right on top of that has to be ground. Okay, and then somewhere in the middle now, you can choose to locate your strip line. Okay, and in this case, I chose this one. And of course, the copper thickness in this case is all 35 micrometers. Okay, where the cores are 250 micrometers or 0.25 millimeter. And then the 2 pre-pregs are 193 micrometers in this case. So you can see that. Of course, I have silk screen on top and bottom, but I ignore that for the moment. I did not include it in the simulations because simply we're assuming that solar mask or silk screen, we don't put that on microstrip works, so it doesn't really affect it. It does not. The other thing now, I have to design vias. How am I going to get from top to bottom? And I did one via here, which basically connects all the way through, plated through via that connects from L1 all the way to L6. Along the way, you can connect anywhere. Okay. And then I have to connect somehow from top to the strip line. So now in that case, now we have to use either blind vias, okay, or use back drilling. And to many of you, some of you don't know what that is. Basically, you have a choice. Now, depending on the cost, you determine which way to go. But in my case, I said, okay, I'm going to use the same one in here and drill the additional stub that is going to be there. So I'm going to go from top to the strip line using the same via here, except do a drill back. Okay, drill this, and that's the technique that you specify, and the PCB house you interact with them, and they know which ones are programmed to do to be drilled. So you drill this so that you get rid of the copper that is here. And the reason we do this is because my RF signal comes in on top, goes down to here, and then goes to the strip line in here, and then goes down to the bottom or comes back up. Now, either way, okay, there's an additional piece of the via that is hanging there as an open stub. And you know, open stub, of course, that's a passive component, and that impacts your signal, and that could kill your signal. In fact, so let's see. Okay, so before we do that, so the two materials, if you go on Roger's website, you know, you've got the 4350. So the dielectric constant is 3.66 for design, okay? And then the pre-preg is 4450, and the dielectric constant is basically around 3.52. So they're not very far from each other. And I have a calculator in here. I calculated the width of the what would have to be 50 ohm on top. If you specify the top layer as being, or the bottom layer as being the microstrip line, it turns out your dimension would have to be, the width is a half millimeter, or 20 mils, okay, or 21 mils, you say. Now, while that stack layer, this stack layer in here, as you can see here, the inner layers, a lot of times they're used for digital and for DC. However, if that is the case, then why should you use expensive cores like the 4350? In my case, I did use that because I have other designs, RF and microwave designs on those sub layers. So in addition to the DC, but you could come in here and you say, well, why should I use cores in the middle that has nothing to do with the RF signal as this expensive low loss material? You could go to FR4, which is cheapest. And of course, yes, you can do. And that's an example in here. You could come in here and you build a stack layer of 6 layers where only top and bottom are basically Rogers 4350s. And that's because those are the ones that are impedance controlled lines, where the lines have to be controlled, or your microchip designs are there. The rest in the middle are all FR4s. So just dwell a little bit and show you the ideas of now. Why am I doing this? Is because let me just show you on the so what I need to do is we have to, as you can see here, we have a microstrip line. This is a crossover that I'm designing right now, which we will go through. So we have this microstrip line that comes in here, and there's another one that goes in here, and then we have in the bottom a strip line, okay? And you can see the strip line on layer 3, and then these are interconnected via 2 vias, okay? So these 2 vias in this case here, as you can see, or let me look on these sideways. Okay, you can see the signal comes in here and goes down and goes over on, travels on L3, and then has to get up back again to avoid this line on top, which is the crossing line, this one here. You see that? Okay, so now the vias, okay, this here, what I did, this is a back drill, meaning the copper was removed, okay, and there's little additional length that is there because we have to keep that because we can't drill so close to the signal line, okay, where of course, let me show you the one, and I'll show you in a minute why. Okay, let's see, here's one. I think this one is the one that, let me just see if it is. This is back drilled as well. Let's just show the one that is not back drilled. Okay. All right, back drilled. Okay. Okay, so here we go. So here's one. Okay, this one here is where we have, okay, we have this line that goes over this line, and we have the vias in here. Oh no, this is back drilled. let's see which one is the one with, oh, no, ground, without. Okay, here it is. Okay, so here's this one in here, where we have the, this line, and we have this line, and then the via, as you can see here. Let me just show you. You can see here, the signal is coming from here, going in, and going on layer 3, but there's this additional stop in here. So the RF signal comes in here and goes out here, but there's this piece here. And in this case, I don't want to use blind vias. And what blind vias are, I'll show you in a minute. They're vias basically that connect the top to an inner layer somewhere and stops. And these are expensive to use. In my case, it was more reliable to economical to just use backdrop. Okay, so let's get back to our discussion on this. Okay, so now let's review what the vias in general are. Basically, we have a via that basically what we call through hole via, which is goes through the whole board and interconnect anywhere along its way, but it commonizes the top to the bottom, okay? And we have not non-plated through hole, which is basically it goes in and it drills through the board. It's a hole without metal on the walls, okay? It doesn't have cylindrical metal. A blind via is where it can connect from top to the inner layer, okay? And it could be done on top here, where it connects this layer to the top, or it could be done to the bottom as well. And we have bedded layer. Okay, bedded layer, that's where you connect. Of course, the gray color here is assumed to be the copper. Okay, the strip line layers, okay, in this case. And so in my case, I said, no, I want to use a via, a complete, a via that has a length equal to the thickness of the substrate. But what I'm going to do to avoid the open stuff, I'm going to use backdrawing. Okay, backdrawing means you remove the additional non-used part of the via. And of course, a lot of cases, people low frequency in DC, we don't really care, so we let that stay there. We don't back drill. And of course, at RF frequencies, that's an open stub. And an open stub, you can see that the impedance of an open stub, as you vary the stub of the length, it can be anywhere inductive. It could, at quarter wavelength, because it's open load, it will be short. And then on the other extreme, it will be capacitive. So it will have the tangent or the cotangent plot that you can see that where it's positive JX and then negative JX, and somewhere in the middle when the stub length is exactly a quarter wavelength at that particular frequency, this will be short. And when it's short, that's deadly, because all of the signal will reflect back with out of phase with your signal, and you get a null. And that's how we build NOT filters anyway in microstrip array. So when you look at the via itself, there's you can model it as being a bunch of capacitors and inductors, and the additional piece that is open, that can be painful. And just to show you the principle of that, this is a diagram that shows a connection between a strip line in here and a microstrip line on top. So the signal goes in here, goes that way, but also goes into the additional open stub. And at some frequency, the reflection back in here, it will be exactly out of phase, and they will cancel with the signal. And that happens at a quarter wavelength. So, and that's determined by this equation in here: the speed of light divided by 4 times the stub length times the square root of the effective dielectric constant of the substrate, okay? And we will see that in a minute. That can really happen, okay? So anyway, let's get back to designing our crossover. So the first thing we're going to do is use, come into the substrate that I chose. And first of all, what I would do is I would lay out a straight line and just make sure that the width that I've calculated is correct and all of that. Now, if you're using ADS, of course, it has a line calculator that you could perform all these calculations. If not, you can use the equations or you can use online calculators. There's plenty of those. Okay, so I ran one experiment where we have a small half-inch line, and you can see that it works fine. It's okay. So, and just to get back to the ANSYS HFSS. So we come with the first experiment is this. As you can see, here's the substrate is built. Okay, the yellowish colors in here. So let's look at it on the side. So I have basically this is one core, this is another core, okay, and this is a pre-preg. This one here. This is a pre-preg layer, and this is a pre-preg layer, okay? And then in the middle, you have, okay, the bottom, you have 1, 2, 3, 4, 5, 6. So that's a 6-layer board, okay? And I have a bunch, I threw in 3 vias on each side just to show that, put those in place for use later, okay? And then here's the line, and you can sweep and see basically the impedance of this line is 50 ohm. So that is here, 47, 46-ish. We can fix that later. But that's good enough for this application. And then if you look at the insertion loss, this is the insertion loss, and it does match the theory. If you go to the line and you find the return loss is good, so that shows that it's a good 50 ohm. Now, as a first experiment, what I'm going to do is build a transition that takes the top to the bottom. So that's basically you come in here and you have a microstrip line, and then you have a via that takes the signal down to the bottom. And then I had 3 ground vias on each side, okay? And now the distance between the vias and between the center via that carries the signal, these are optimized. You basically sweep these dimensions and get to a point where this is good. So this is what I got, and you can see the electromagnetic E field going in and through the center via, which carries the signal via, and then the ground via. As you can see that they're bounding the E field from spreading to the sides, which is good, and that's what we want to see. So that experiment is here. So basically, what we have a line on top, okay, and then we have a line on the bottom, okay, and then we have a via that interconnects them, okay, and the via, of course, in this way, I designed the via, which is basically 2 cylinder metals, one smaller than the other one, and you subtract them so you can get the finished drill hole, and then you make the pads. Basically, at each layer there's a ring pad, and then the anti-pad as well. You design that, and that's basically. If you come to my training, we will go through these exercises. So this is basically what this is doing. Okay, so let's look at the sideways. Why we do this? Because this is part of building a crossover, because we either crossover by going into from top to strip line and then back up on top, or we go down, we go top, bottom, and then back up. So in this case, I chose to do both, and I'll show you that in a moment. So let's see the frequency response. So this is, I swapped it, and you can see that the loss is at some frequencies way up in the 28 gigahertz is about 0.27 dB. It has a little ripple in areas where it gets to be as high as 0.6 dB. Okay, and that's typical for these transitions. You can tweak this to be lower, but that's what we got right now. So let's look at the E field. Oh, this doesn't have an E field running, so let's run, we have to run this again. So let's run this again. All right, this should take a moment. Okay. Okay. Okay, this take a few seconds. Run. Should be done by now. Okay, here we go. Started to give us some results for the E field. Okay, so you can see the E field. Let me take out the highlighting on the, okay. So you can see the E field. It's coming on one side through this, the microstrip line down the via, and then to the other side where the other microstrip line is at. Okay. So if we animate this, it's still running. Can't animate while it's still running. So let's see. Still hasn't converged yet. Now, as you can see here, that there are two metal ground copper pore areas where these are, one might ask, how did you come up with those? Those are really intuitive for those people that do layout, even people that are not electrical engineers, just basically, you know, a lot of companies, you got women, especially females, become really good at doing, because it's artistic, doing PCB layout. And a lot of them, they learn almost intuitively that, yeah, we need a copper pore in this area and we need ground vias. And even a lot of engineers, regardless, males, females, but if even if they're not RF engineers, when they do layout, they along the years they get so much feedback from microwave engineers that they become really good at knowing where to put these things. Okay, so for instance, I know that the signal's coming this way, so I want to make sure that it doesn't spill over here. So for sure, you build a little dam made of copper conductor in here, and you make sure that it's spaced away at least 2 or 3 times the width of this line here, away from here. Okay, let me get rid of this. Okay, so you can see that, let me, okay, so you can see that, you know, intuitively you think, well, the signal is coming this way and has to go over and cross. So I really want to make sure that it stops here, and any leakage would be grounded right there. And that's where you have these here and the vias that you see on here along the signal via. Okay, and then the other side, which is, let me get the other side. So you can see these metal pieces in here are all working together to make sure that the signal is preserved to stay only in this area, so that you can come in from top to layer 3 or to the bottom in this case, but cross over and go through, clear from all layers and end up in the bottom without any interference. Okay. And so let's look at the E field again. Okay, let's look at the signal here. Okay, we look at the, so what I'm going to do is we're gonna halt right here and continue in the other layer, but in the other video. But essentially what we want to do, we want to get back to get to this point where we are designing a complete crossover device like this one here, for instance. Okay, this is one that I designed, which is very similar to the ones that you see offered commercially, like these ones. Okay, or like this one. Well, this one is one way. This is more like this type where you have two signals. Okay, and that's what we're gonna get. We're gonna get to this part where we design this one here. Okay, so until the next video, please tune in. I'm gonna upload that right after this one to make it not so long. Okay, this is Dr. Mohammed Nizami, thanking you again. I appreciate your watching this video, and we will see you in the next video. Thank you very much. Have a great day.